Hey everyone. Hey everyone. Hey everyone. Hey everyone. I think I've gotten stuck in a loop. What's going on? Oh, we're looking at a fractal. Look at that. It just kind of keeps going and going and going. Oh, it's getting weird. Okay, well, you know what? Let's have a little look here. Okay, oh, there we are. Okay, hi. We are back with another fantastic lesson in the chapter of geometric sequences and series and exponential functions and graphs and all that sort of stuff. So far we've looked at geometric sequences, and now we're going to look at geometric series, and we're going to explain what the difference is between the two in just a sec. I showed you this little picture here, or a GIF or a GIF. Okay, let's fight about that one. The animation, which actually shows a fractal. If you don't know what a fractal is, it's pretty nifty. I'm just going to go share my screen again, but I'm going to share my entire screen just so I know everyone's seeing what I can see. I'm going to make this bigger. This is a fractal pattern where we can see a repeating, recursive situation going on, where when we zoom in on one part, it just looks like the same part over and over and over again. So this is a pretty neat little situation. What this has to do with what we're learning here, I'll show you in just a sec. First, I want to click on this website. So this is another website here. I'm going to just close that one. This website here is this. Oh, you can see all my internet history. Oh, there you go. Oh, SC2Cast, Amazon, Gmail. Wow, yeah, I got lots of great stuff. Oh, Realtor, Facebook, YouTube, all the big ones. But it's andrewwanghoyer.com/experiments/fractals. I'll put this in the description so you can actually have a look at it yourself. It's a really neat website. This is an interactive website with fractals, and what it is it's a way you can interact with these repeating patterns. So we've talked a little bit about this Cantor set in the last lesson here, and this is a way you can actually visualize it quite well. What we learned in the last lesson is this is a geometric sequence. The length of the lines can be considered a geometric sequence. You could also consider the number of lines. If you actually notice, the first row has one line, the next one has two. I can't move my mouse over them because that moves the whole thing. But then the next one has 4 and 8 and 16. So one thing we could use geometric sequences for is we could ask a question like, what's the length of the lines in the 12th row? Or we could say, how many lines are in the 12th row? But a more unique, interesting question could be to say, how many lines are there in total? Or if I put all these lines, chalk them up and put them all in a row, how long would the line be? There's a lot of different things you can look at when you're not just counting how many there are in any one iteration or in one repetition, but how many are there in total when we're going up to all the iterations and including every single step along the way. So in this situation, what would it be like if I asked you how many lines are there in total? Well, you could count the first row and you could say, well, there's 1 in the first row, and you could add to it 2 in the second, so you'd have 3. Then you'd add 4 more to get to 7, and then you'd add down here you'd have 8 more, so you get to 15, and you can see pretty quickly that the math's can get pretty hard. And if I asked you how many lines are there in total, and I kept this going, I mean, we can only see 7 rows, but maybe we could think of this going infinitely, or maybe to 100 rows or something like that. We want a way of thinking about how can we actually add that up in a systematic way. Everything we're doing in this little chapter here, it's all about systematic ways of thinking, where you're not just simply going, okay, well, 1 plus 2 plus 4 plus 8, and so on like that. So we're taking logic, but we're also just adding a bit of pattern seeking and mathematical rigor to it. So here's a fun little question. How many lines are there? If you want to take a second, think about that, you can do so. And you might actually notice there is quite a pattern. It has to do with powers of 2. Anyway, so what we're going to do is we're going to look at this. There's a whole bunch more. There's a Pythagoras tree down here, which is pretty neat because you can look at this and it's really beautiful, actually. If you move your mouse around, you can see how this actually grows and shrinks. And this, not surprisingly, looks a lot like nature. And there's actually quite a big connection between nature and math. Maybe that's surprising, maybe it's not, but it definitely is there. And depending on how I move this around, I can make a whole bunch of different things. Hey, there's, was that broccoli? This kind of looks like something you see growing in like a body of water somewhere, like some seaweed or something like that. It's pretty neat. Anyway, there's a whole bunch more. There's snowflakes you can make there, and this is one of my favorites, the H tree, which kind of looks like satellite dishes and stuff. And again, that looks a lot like a tree. Here's another one, and so on. Okay, so what you can do later is have a look at this if you want, because it is a very curious thing, and I'll be asking you some questions based on this kind of stuff as well. This is not the only application of what we're going to be doing, but it certainly is one of the most interesting ones. So without further ado, let's have a look here at geometric series. We're going to learn the basic math behind what we're doing here, and we're going to apply it to some interesting situations. But first, the basics. Okay. So as you can see here, a geometric series is the sum of n numbers in a geometric sequence. So it's a really simple concept. We're going to abbreviate it with S with a little n down there. N would be the number of terms. S stands for sum. So if you have a geometric sequence and it goes 2, 4, 6, 18, the series would be 2 plus 4 plus 8 plus 16. If we wanted to figure out what the sum of the first 4 terms would be, we could actually say S4. And then we would understand that it would be 2 plus 4 plus 8 plus 16. And of course, if we wanted to say S5, we would understand that to be 2 plus 4 plus 8 plus 16. And I guess the next term would be 32, so we'd add it all together. Whoops. So the sum is an actual number, whereas a sequence is just a list. A series actually adds up to something here. I'm not even going to try and do that math in my head. I know it's not hard, but you know how things are when you're put on the spot. So let's have a look at this formula. This is the next piece here. If you actually tried to do all of this, this is not that hard. I mean, we could go 32 plus 16 plus 8 plus 4 plus 2. But if I start asking you questions like, what's the sum of the first 10 terms? You'd be like, ugh. So this formula here is going to help us out an awful lot. Now just take a second, stare at that formula, and just appreciate what it is. First of all, let's just define something. So Sn is the sum of the first n terms. T1 is the first term. Again, a lot of resources use A instead of T1. And again, I'm not 100% sure why that is, but that's just something you should be aware of. R is the common ratio, n is the number of terms. So like all things in math, this is a formula and it came from something. It's not really super important to see the derivation, but if you're curious, I did include it here below and you can have a little look. And this was just stolen as a Google image thing. So credit to someone out there in the land of Google images, but it went on the internet, so I'm going to take it. So this little s here stands for sum. They're using lowercase s instead of capital S and a instead of T1. But you can see a sum, a geometric sum, would be a plus a times r plus a times r squared, cubed, and all that. And then a times r to the n minus 1. Remember, this is how we would actually calculate the last term, right, using our formula from last time. The clever kid who came up with this realized that if you multiply every term in the sum by r, a becomes a times r, ar becomes ar squared becomes ar cubed, and the very last term, ar to the n minus 1, becomes ar to the n. And then if you take these two and you subtract them, and if you actually imagine just putting a big line under this and you subtract it, you'd actually be subtracting, like in these columns here, we put in these columns for a good reason, because AR minus AR, they disappear, they disappear, they disappear, 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 everything else disappear, everything in between disappears. And what you're left with is this and this. So S minus RS, keep in mind there would be a 0 up here, right? So 0 minus AR to the n would give negative AR to the n. And then, of course, we can factor out S from the left side, and we can divide this term down to the other side to get this. Now, if that was all kind of fast, feel free to go back and watch it again, but it's not even super duper important you remember that. I'm never going to ask you to derive that again, but I did want to at least show you where it comes from. There's one catch here, r is not allowed to be equal to 1. This doesn't work if r is equal to 1. And by the way, that's not a geometric series if r is 1. If r is 1, that's like saying the first term is 2, and then you multiply that by 1 to get the next term, which is 2 and 2 and 2 and 2 and 2 and so on. There's actually a way of summing that up, but you don't need a fancy formula. You just need to take 2 and multiply it by the number of terms. Anyway, there you go. So there is the geometric series formula all the way up there. That's the nice result. These people, again, they have A. The brackets are in a little bit of a different position, but whatever. Okay, so quick little example here. Determine the following. If I had a geometric series going 2 plus 3 plus 4 plus 5, and I wanted to know S12, this is like saying the sum of the first 12 terms. So what that would look like is that would be like S12 equals 2 plus 3 plus 4.5 plus the next term. And again, I don't even want to think about it, but I can tell you, I do know R, the repeating ratio here. So to go from 2 to 3, you have to multiply by 1.5, or 3 over 2. And again, from 3 to 4.5, same thing, multiplied by 1.5. So we can confirm that R is the same, which is important. It has to be the same. And then what we can do is we can use our formula. So we know in general, Sn equals T1, 1 minus R to the power of n over 1 minus R. So if I'm looking for the sum of the first 12 terms, I take the first term, which is 2. I go 1 minus, and here I'm going to write 1.5 to the power of n, which is 12. And then I'm going to go 1 minus 1.5. A thing that a lot of people kind of get used to is when you're doing geometric sequences, they remember that this is Tn equals T1 R to the n minus 1. They get used to that exponent being n minus 1. This one is just straight up an n, so just be aware of that. Okay, so when we have, oh good boy, okay, we got to work this out. Now here's the thing, the odds of you working this out without the calculator are almost non-existent. I mean, you definitely can. If you really wanted to power through this, you could go to fractions, and you could say something like 2, 1 minus, okay, this would be like 3 to the power of 12 over 2 to the power of 12, and then the whole thing would be divided by -1/2, and but that's really hard. So we're just actually going to use a calculator here. So I'm just going to jump over to my calculator, and I'm going to type in this. So the way I'm going to do this, I'm going to go 3 to the power of 12, and I'm going to divide that guy by 2 to the power of 12, and I'm going to push equals. Okay, so that's some weird thing here. I'm going to go 1 minus that answer. Now, can I easily do that on this calculator? Okay, so you know what? I'm actually going to switch things around slightly. One modification you can make, by the way, if you don't like the way this is written, you can actually sometimes do it this way. I'm going to erase this because this is not something I'm going to do. Sometimes, if you find it more useful, you can switch the signs of everything. So you can write it like this here. And if that makes life more useful or simple for you, then go ahead and do it. So what we can do is, I've worked out 1.5 to the power of 12, and I'm going to subtract 1 from it, which is obviously just that. I'm going to multiply that by 2. I'm going to push equals, and then I'm going to divide it by 0.5. And I accidentally hit the wrong button, so I'm just going to quickly retype that in. I'm just going to use 1.5 to the power of 12. Okay, minus 1 equals times 2 equals, and then divide by 0.5. Okay, so anyway, so we work this all, and we get 514,985. Okay, so this equals 514.985. All right, so normally it's not that hard because, and I've already forgotten the number, because you've got a better calculator than the stupid Windows one. Anyway, there you go. So now we just take a second, we think, is this even a reasonable number? Did I screw up colossally, or does it make sense? When we think about the numbers we're adding together, 2 plus 3 plus 4.5, the next number is going to be 6, and the next number might be like 9, and the next number might be 12, 13, 14, something like that. Does this sound reasonable that when you have 12 of those numbers, you get 514? It's within the realm of possibility for sure. So I'm inclined to believe that. Okay, moving on to the next one. Find the sum of this. So the one thing about this question, the reason I picked this one is because in this case, there's a ... You actually don't know what the number of terms is. How do you figure out the sum of n terms when you don't know what n is? And you got to do a little bit of work to figure it out. So the way we're going to look at this is going to be something we're going to focus on later, especially when the numbers get harder. But right now, we're just going to think about this as, if we notice a pattern, 8 plus 4 plus 2, the next one's going to be 1, the next one's going to be 1 over 2, 1 over 4, 1 over 8, 1 over 16, 1 over 32, and 1 over 64. Okay, listing it all out right now is okay. There's definitely better ways of doing it. Let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so what we have is n is equal to 10. There's definitely better ways of doing this, but we'll look at those later on. Those of you who are really curious, wondering, what is the better way right now? Well, I'm going to show you, sort of. Okay, what is a 64? 64 is 2 to the power of 6, so this is 2 to the power of negative 6 here. So we're kind of thinking in terms of powers of 2. How many times do we have to go from here, here, here to go from 3 to negative 6? That would be 9 skips, which would make 10 terms in total. Anyway, we're going to worry about that later. Okay, so now I figured out that n is 10, and what we have is we've got the sum of 10 terms equals, so we need t1, we need 1 minus r to the power of 10, and we're going 1 minus r. We can see what r is as we're moving along. R is equal to 1 half, or 0.5. Maybe 1 half is a better term. T1 is equal to 8, so if I go 8, 1 minus, okay, so I'm going to have to put 1 half to the power of 10, and then the bottom is 1 minus 1 half. So in this form here, we have basically 8, and then 1 minus 1 over 2 to the power of 10. I'm just simplifying it a bit, and then the bottom is equal to a half, or 0.5. So again, this is something you could maybe attempt to do without a calculator, but it's going to be a little challenging, so I'm just going to jump out of here, and I'm going to go calculator, and then we've got, let's see, 1 divided by 2 to the power of 10. I really hate this Windows calculator. And I'm going to go minus 1 here, and then I'm going to times that by 8 equals, and I switch the order around there, so I'm going to divide it by 0.5, but I'm going to make it, oh, I was thinking I was going to make it negative, but it turns out it's already good. I think I screwed up again. Boy, this is really a terrible calculator. 1 divided by 2 to the power of 10 equals that. Okay, so if I go minus 1, I should get a negative answer, which is what I have. I multiply it by 8, then I divide it by 0.5. Oh, that looks better. I think I screwed up before. And I switched the order from the 1 here. I switch these around for the sake of just making it easier to type into the calculator, so it's not a negative number, it's actually positive. And I'm just going to take the positive version of that. And again, just use your own calculator if you have a good one. 15.984. Okay, so 15.984, and it keeps on going, but it's about almost 16. Now you take a sec, does that make any sense? You're adding numbers like 8 plus 4 plus 2 plus 1. So even 8 plus 4 is 12, plus 2 is 14, plus 1 is 15, and then 15 and a half, and then 15.75. There's no way we're ever getting higher than 16. So 15.984 makes some sense. Okay, this question here, if S4 equals 30 and R equals 2, find T7. This is just a weird random one, but I thought I'd throw it in here as something a little different. So we know S4 is equal to 30. We know that R is equal to 2. And we're asked, what is T7? How the heck do we get T7 when we have a formula like this? So you'll notice, of course, nowhere in this formula can we find T7, but we can find T1, and we can remember that this is a geometric series, so we can use the geometric sequence formula to figure out T7. So I think what we're going to do is we're going to solve by finding out what T1 is equal to, and then we're going to work out what T7 is. So this will be 2 to the power of 4, this will be 1 over 2, and the first term we don't know, S4 we do know, so I'm actually going to go ahead and just switch that out with the sum, which is 30. Okay, so now we just formed an equation with one variable, and we've got to solve. So we're going to take this to the other side. 1 minus 2 is negative 1, so when I bring it over here, this will be negative 30 equals T1. 1 minus 2 to the 4, 2 to the power of 4. I think this one we can do with our calculator calculators in our brain. So 2 to the power of 4 is, let's see, 2, 4, 8, 16. So this one I'm thinking here. So this is actually going to become T1 times negative 15. 1 minus 16 is negative 15. So what we can figure out is T1 is equal to 2. So the first term is 2. And then if we know that, then we could say, well, T7 is equal to T1 times R to the power of 7 minus 1. So we can go 2 times 2 to the power of 6, which would be 2 to the power of 7, and 2 to the power of 7 would be 128. So the 7th term would be 128. Okay. All right. You know, I sort of debated it making this all about coronavirus because it turns out that what we're experiencing right now, this whole pandemic, this is actually a geometric progression. This is an exponentially growing disease, as you've probably seen in some of the graphs if you've had a look. I decided I wouldn't make this all about coronavirus, even though it's a worth thinking about, but I thought just generally diseases, because once we're done with this and we forget about coronavirus, we still have the idea of disease spreading. It's a big thing. It's going to feel like part of our lives for a while now. So here's a little bit of a research question. So I actually did a little looking here. The basic reproduction rate is abbreviated as R with a 0, or R naught is how you would actually pronounce it. This is actually a number that's well known to disease specialists, epidemiologists, and all that sort of stuff like that. This is how many people who catch the disease when they meet up or have contact with one contagious person. So as an example, if R naught is equal to 3, then one person with the disease will typically spread it to 3 other people. It's just an average. Of course, it's not a guarantee, but that is how things work on a large scale. We can count on averages. Here's a little graphic. This is actually absolutely true. So hepatitis C has R naught value of 2. Those might be a little tiny bit hard to see, so I'll just write them in a little bolder. 2. Ebola is 2. HIV is 4. So the typical HIV patient actually spreads it to 4 people. SARS, if you remember SARS from a long time ago, which was similar to COVID-19, that was 4. Mumps is 10, and measles is 18. By the way, you can thank people for having vaccines for these, especially these last 2. These have vaccines, so you can thank people who actually get their shots. A little jab at the anti-vaxxers out there, but there's a reason why we're not all overrun with measles, and we will have a vaccine for coronavirus one day too. And if you're wondering what is R naught for coronavirus, I did a little bit of reading. I think it's around 2 to 3, although it can kind of vary. So now, the thing about this is it doesn't tell us anything about timelines. It just says if one person gets infected, chances are, if they had HIV, for example, chances are they're going to infect 4 other people at some point. So I'm sort of forcing this a little bit by saying if we assume an infected person with measles spreads the disease once per day, that's not a guarantee, but let's just say they did. They go out and meet their friends once per day or whatever, and then all of those friends meet someone once per day. How many people will one infected person get sick in total after 2 weeks? So what this is basically saying is you start with, let's have a look at the number of infected people. So the number of infected people on day 1, you're going to have one person, right? So one person catches measles, and then they go and they meet a bunch of other people. So what happens here is they're going to, that's day 1, and then day 2, they're going to meet up with someone, and they're going to infect 18 other people. But they themselves are still infected. So on day 2, there's going to be 18 people plus the one who is already infected. Then on day 3, all those 18 people are going to meet up with 18 other people, because that's what the average spreading rate is. So you're going to wind up having 18 to the power of 2, or 18 times 18, right? If 18 people infect 18 people, it's 18 times 18 people. And pretty quickly you can see how this progression is going to go. So it'd be quite challenging for us to go ... all the way up to day, 2 weeks, so day 14. It'd be challenging for us to add up all these numbers manually, but we could definitely do it using a geometric series formula. So let's just have a little look here. if you had the sum of 14 terms, so the amount of infections on day 1 and the amount of infections on day 2, and you added them all up, this would be an adding thing. This wouldn't be a sequence problem because we're assuming these people from day 1 are still sick, so we're going to add them up as additional people. We would have T1, 1 minus r to the power of 14 over 1 minus r. So you're going to start with one person, but then this is going to spread. R is 18, right? We're multiplying by 18 every single time. And we're going to raise that to the power of 14. If you know anything about numbers, you know we're in for a very, very large number. So let's just go and have a look here. 18, let's go to the calculator. 18 to the power of 14. Okay, well that's a lot of people. So what we have basically is looking at this. If you'd like, I could subtract 1 from it because that's part of the formula. And then I could even divide it by 1 minus 18, which is 17. So let's divide that by 17. That's not going to knock it down too much, but there we go. So what do we have here? Let's see. So right here, that's thousands, millions, billions, trillions. I don't even know what that thing's called. This is the time for scientific notation. That's going to be 2.2 and 16 zeros. Okay, so that's 2.2 times 10 to the power of 16. So that is by far every single human on Earth getting infected with the disease. So if that sounds a little scary, you know, that's how things can happen if it was totally mathematical. Of course, this isn't what really happens. There's vaccines, there's immunities, there's human interventions like social distancing and all that sort of stuff. So not everyone's going to catch it. But this is what would happen in 2 weeks if all of those measles people just went out and kept spreading and spreading and spreading. So if you think about what this would look like even for coronavirus or anything else that's less contagious, measles is more contagious, or at least historically has been because maybe people just spread it more. We're still going to have quite a large number. Anyway, so that's the importance of taking care of it early. If you knock it down and you don't let this happen, you don't let it spread for 14 days, but you let it spread for only 3 days, well, if you look at that, you're going to be in the hundreds rather than the quintillions or whatever it's called. Anyway, moving on. Okay, so we have another little bit, which is an extension here. We have infinite series. So we can think about a series that never actually ends. So you add numbers, you go like 1 plus 2 plus 4 plus 8 plus 8, keep on going forever and ever and ever and ever. It never ends. And you could then ask the question, what's the sum of that? And if you're looking at this going, well, this is sort of weird because won't the sum of this series be infinite? You'd absolutely be correct. So you can't always figure out a sum, but you can if you have these very specific conditions. So let's look at what they are. If a series has n goes to infinity terms and r is between -1 and 1, so r is going to be like a decimal or fraction. The series formula can simplify down from this complicated beast, which isn't that complicated, but it simplifies down to this. There's an infinity symbol there, by the way. So if you're thinking, what is the difference between these two? It's very simple. This first guy disappeared. So we're left with T1 over 1 minus r. And the reason for this is actually really, really, really quite simple. Take any number you want. Take the number 0.9, as long as it's less than 1, and raise it to the power of 1. It's not going to change. But raise it to the power of 10, and this is going to be small. In fact, 0.9 to the power of 10, we could actually work that out. We could say that 0.9 to the power of 10 equals 0.3. We could go 0.9 to the power of a big number, like 10,000, and now we've got 2.66 times 10 to the negative 458. Basically, that's 0. What's going to happen here is any number, as long as it's less than 1, if you raise it to the power of infinity, it's basically 0. Now, if the number was equal to 1, 1 to the power of infinity is 1. If the number is 1.1, this, it goes all the way to infinity. It's quite astounding at what a difference it makes here, but you can just understand about numbers. If you're multiplying by a number less than 1, it gets smaller. If your number is bigger than 1, multiplying by that, it's going to get bigger. So as long as the number is less than 1 or greater than -1, then we can have this formula here. This guy just disappears. R to the power of n, r to the power of infinity equals 0, and he's gone, and then 1's gone too, because you just don't even need to multiply by 1. Anyway, so the whole formula simplifies down to this guy, and it's really great. This is because r to the power of infinity, yeah, okay, so this is what I just said. If you have the situation, now the simple way of writing it is the size of r, so the absolute value is greater than or equal to 1. Then the series has no finite sum because the terms keep getting bigger. So let's just look at a couple examples here. What is the sum of the infinite geometric series? So the first thing you have to do with these types of questions, you have to look at this and you have to make a decision. Is this even possible? We can see r is equal to a half and a half and a half. So since the size of r is less than 1, I'm using absolute values because it's a little simpler than writing it like this every time, but it means the same thing. Then you can use the sum of infinite terms formula. So this is a really simple formula here, and it's quite amazing how it works. 1 minus 1 half. So I don't need my calculator for this. This is much better. These are much cleaner to work out. 1 minus a half is equal to a half. 40 divided by a half is the same as 40 times 2, which is 80. If you took these numbers and you kept adding them forever, you will get to 80. And this is really quite an interesting result, because if you notice, we started with 40 and we're cutting its successive numbers in half. If you want a sense of why this works, like in terms of a drawing, you can think of it this way. Here's 0, here's 80. The very first term is at 40, and that's half the distance, right? So there we go. And if you add half of that, so half of 40 is 20, and we're going to add half the remaining distance. That's going to get us to 60. And then we add half the remaining distance. We'll be up to 70. And then we add half the distance there. We'll be at 75. And we keep adding half the distance. Half. You might sit there and go, well, if we're always adding half of what's remaining, are we ever actually going to get to 80? And you might argue realistically no, but we're thinking math, so infinite means infinite. And if you keep doing this infinitely, your lines will get so close together, we'll basically actually reach the number 80. Here's another one. Is it possible to calculate for this guy? So we can see 1 multiplied by -3. This one would be multiplied by -3 and so on. We can see that r is equal to -3. So what we could deduce is if you sit there and you just blindly use the formula s infinity equals this, and you do this whole thing, this would be 1 over 1. By the way, this is the wrong way to do it, so don't be paying a bunch of attention to this. This would be like 1/3. Does this even make sense? 1 minus 3 plus 9 minus 27. Because the next term is going to be plus 81, the next one's going to be minus 243, the next one's going to be whatever that is, 729, I think. How can you end up with a number like 1/3 by doing this? What is the last number? Each number keeps getting bigger. The next number is going to be minus, and it's going to be bigger than that. And the next number is going to be plus, and it's going to be bigger than that. It's actually going to oscillate between a big negative and a big positive, and even a bigger negative and even bigger positive. It's not going to make any sense. So this formula absolutely does not work. You cannot use this formula when r is greater than 1. So since the absolute value of r is greater than or equal to 1, you can't evaluate s infinity. Okay, here's one more question. This is an interesting little result here. When you have repeating decimals, those are actually geometric series. So let's have a little look at how this makes sense. If you think about this, 0.22222 repeating, this is actually 0.2 plus 0.02 plus 0.002, and it keeps on going. Okay, so this is one way you can actually represent a repeating decimal, so you can think of it this way. You can even make this more obvious by making this 2 over 10 plus 2 over 100 plus 2 over 1,000, and so on. So we can see what's happening here. R, we're multiplying each term by 1 over 10. So if we want, we can actually write this using our formula, and we we can figure out that if the first term is 0.2 or 2 over 10 and r is 1 over 10, what we can see here is we go 2 over 10 divided by 1 minus 1 over 10, which is 9 over 10. Well, this actually simplifies down. By the way, if you're really bad at doing this, you can always flip and multiply here. Okay, so we can actually see this is equal to 2 over 9. And if you grab your calculator and you type 2 over 9, and we'll just do it here because why not? We'll go to a calculator and we'll go, okay, delete 2 divided by 9. Well, there we go, 0.222222 forever. Okay, so what we just did is we just figured out a way of going from a repeating decimal, and we can use our infinite geometric series idea to figure out the equivalent fraction. So it's pretty nifty. You can do it for another one over here. This one, by the way, if you have to do this one, there's just a slightly different approach. You want to think about what units are repeating. So you don't go 0.4 plus 0.05 and so on. You actually want to go 0.45 plus 0.0045 plus 0.000045 and so on. What we can see here is the first term is actually 45 over 100. The next term is 45 over. Instead of going, oh boy, I could go 10,000, and it's 10,000 because you got to go 1, 2, 3, 4 spaces. I don't want to do 10,000. I'm going to write this as 100 squared. And then this one, what do you think this one is? It's going to be 100 cubed. It's 100 cubed because it's like there's 100, there's 100, there's 100. Okay. So what we can see here is we've got a similar situation, except in this case, r is not equal to 10, it's equal to 1 over 100. So in a similar fashion, we can write our formula here, and we could say that T1 is 45 over 100, and then this is 1 minus 1 over 100, which is 45 over 100 minus 99 over 100. And that simplifies to 45 over 99. If you don't believe me, go to your calculator and type it in. Clear that, 45 divided by 99, boom. Okay. You might even notice there's a bit of a pattern here if it's like a 4545 repeating, where the repeating happens in digit clumps of 2, then it's divided by 99. If it was repeating digits of 3, like 1, 2, 3, 1, 2, 3, 1, 2, 3, then it's going to be over 999, and in fact 0.123, like 0.123, 123, 123. I can almost guarantee you, just by looking at this, it'd be 123 divided by 99. So let's actually just try it just for fun. 123 divided by 999. I think I said 99, I meant 999. There you go. Okay, so I don't necessarily know if that's something you would memorize. I think it'd be more useful to figure it out, but that's a nice little interesting result. Okay, so I will leave it there, and thanks for watching. See you next time.